guys, welcome back. Do the same thing that we did last time. I want you to go ahead and turn the lights off, sit back, and just enjoy the pictures and what's going on within these stars. So guys, today we're going to talk about the evolution of stars, and that basically means moving off the main sequence line. Remember that stars in the main sequence line are certainly converting hydrogen into helium, and they're doing what they're supposed to. But first we need to take just a second and talk about a gas pressure and the ideal gas law, because we're going to have to look at what's going on within that core. So a normal gas has properties that include temperature, pressure, and volume. If you remember back to your chemistry, you might have talked about the ideal gas law, PV equals nRT, where P stands for pressure, V stands for volume, N is a number of moles, basically the mass that you have. R is just a constant, and of course T is the temperature. As the pressure increases, so does my temperature, and when my pressure increases and my temperature increases, the volume then there goes ahead and decreases. And we can't really change one without the other. And so when we start talking about what's going on in these cores, we'll come back and talk about that pressure and that temperature and that volume, and we'll see what happens when those cores respond. But remember, guys, you can't really change one without changing the other. So at the end of the star's time on the main sequence, that core is going to be consisting of basically helium nuclei mixed with electrons, and it's going to behave like a normal gas or a plasma. Fusion is going to slow, gravity is going to take over, and it increases the pressure and the temperature. And remember, when gravity takes over, everything's going to go ahead and start collapsing, and that's why then your pressure increases as well as your temperature. Now, we find, too, that as a star reaches the end of its time on the main sequence line, their luminosity is going to increase a little bit. It's going to kind of be a little bit of a variable star because of that kind of slowing, and then you're going to find some more hydrogen to make some helium, things like that. And so as that reaction starts kind of slowing down, that's going to cause the core to collapse, which again is going to turn that gravitational collapse into energy, and the star is going to end up expanding a little bit and to become cooler. Now, that means that what happens on that main sequence line, I mean, I've always drawn it as a nice line, but in reality, it's actually more broad than it is just a line, because you're getting some of this, variability or instability then toward the time that the star is finally going to be moving off the main sequence line. Now, we've talked about brown dwarfs. Remember, they're less than about 0.08 solar masses. And remember, they're never going to be able to reach the temperatures necessary to really begin hydrogen burning. And so that's why you always find them right below that main sequence line, because they're actually never going to make it. And so basically, guys, they're just simply going to cool down and completely fade away. Red dwarfs, on the other hand, are those very low mass stars that are in the lower end of the main sequence line. And they're between about 0.08 and about 0.4, so they're smaller than what our sun is. And they're going to go ahead and form large convection currents within the layers after that hydrogen burning occurs, and so you get that heat that's distributed through the red dwarf because of those big convection currents. You can kind of see here you've got that core, and then on the outside you get that really big convection currents that are occurring. But that core itself is more of a convective, so you're bringing heat to the outer edge of the core, and then, of course, that then is going to bring energy to the rest of the envelope of the star. Those poor little stars, their energy output is so low, you're really never going to be able to get to the point that you're going to be able to burn helium or anything else. So the core is going to run low on hydrogen. That fusion rate's obviously going to slow. And, the core contracts because that star is so small anyway, it's never going to be able to go through the kinds of reactions that we're going to see our sun go through, as well as all the stars that are a little bit more massive than our sun. And so because you have those convection currents that are carrying away the heat, we're going to talk about something later on called hydrogen shell burning. That's not going to happen. You're never going to reach the temperatures necessary to do anything else. And so they're going to just kind of slowly fade away. So what's going to happen as that star contracts, it's going to actually move toward the white dwarf part of the region of the HR diagram. But we know that these stars, remember guys, that the smaller the star is, the longer it's going to be on the main sequence line. And so these red dwarfs are never going to get to the point that we see the white dwarfs now from those red dwarfs. Okay, so we know those things, we've not been around long enough to really see that evolution of those red dwarfs. So that means that the white dwarfs that we see right now can't have come from those red dwarfs. So we have to come up with other mechanisms to explain why on our HR diagram we do see those white dwarfs. So like I said, guys, eventually those red dwarfs, and I do mean eventually, in a really, 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 really far distant time, will just basically cool off. Now, we're going to talk about stars that are obviously bigger than 0.4 solar masses, and they're going to become giants or red supergiants, and how they get there is completely dependent upon their original mass. And so this picture just gives you a feel for how big some of those stars are. Now, guys, I want you to realize that on this scale, if you look at the bottom left, you see something that says the sun, and it has in parentheses 1 pixel. We can't even see the sun. If we had to look at that, we'd see it as 1 pixel size relative to these big stars. You can see Sirius down there. You can see Pollux. You can see Arcturus, Rigel, Aldebaran. And then, man, look at those other 2 stars. Those are red supergiants. It gives you a feel for how big those stars are compared to our poor little 1 pixel sun down there. And yes, our star will eventually go ahead and form a red giant. It'll never get to the stage that Antares is, because Antares is much, much larger to start with. But remember, guys, we're not adding any mass. We're just going to cause that expansion to occur. So let's talk about something called hydrogen shell burning. So in that core, we're converting hydrogen to helium. Well, what happens is most of the hydrogen that gets converted into helium is within the inner part of the core. And so the outer part of the core still has hydrogen there, but it doesn't have a lot of friends there to go ahead and get together and convert hydrogen into helium. So you just basically have a lot of hydrogen with a bunch of helium within that core. And that's then what happens when that core goes ahead and starts slowing down. And so when the core then is not producing as much energy, of course gravity takes over, the core collapses, the core then heats up, and as it heats up then, before it starts burning helium, it goes ahead and starts burning that hydrogen that's in the shell, right around that outer edge of the core. And so that energy that's coming from now the ignition of the hydrogen around the core is going to go ahead and cause the outer layers of the star to expand and to go ahead and cool off. Because remember, eventually, whatever happens in the core will happen to the rest of the star. And so that energy production then moves through the star, and the star expands. And as it expands, remember, guys, something that expands cools off. And the other thing that then, as it cools off, is going to then become that redder color. And the further out the envelope of the star is from the core means there's less gravitational attraction. So those outer edges are not held on real tightly. And that's certainly going to affect what happens when we talk about our sun becoming a planetary nebula, because then those outer layers are basically leaking off. And they leak off in really, really, really cool patterns. So basically, as the star expands that first time, if we're thinking about our sun, it's going to go to about 0.5 astronomical units. So it's going to be about halfway between us and the sun when that thing expands. So guys, poor Mercury is gone. I mean, it's not there at all. And Venus is going to get a whole lot hotter than what it is right now. And every time we do have a pulse, what's going on within that core, then again, that outer envelope of the star is going to go ahead and expand. Now, let's go ahead and think about what happens to medium-sized stars, certainly stars that are like our sun. And a medium size, as you can see, from about 0.04 to about 4 solar masses. And we find that for the smaller medium-sized stars, they're going to go ahead and start burning helium one way. For the larger stars, that 2 to 4 solar masses, they're going to start burning helium another way. And really the difference is the explosiveness of how that helium burning starts. And I want you to, like I said, think about matches versus detonations of 1,000 nuclear bombs. Guys, that's a huge energy difference. And that's exactly what goes on with these smaller stars when they start burning helium. It's called a helium flash, and you get a tremendous amount of energy produced, in which case you get a big, huge pulse, as opposed to looking at just the kind of a burning of match. And that's how these larger stars do it. And so it's not a really big deal. Remember, guys, we're going to find out that every one of the elements that we see in this periodic table is produced within a star, either within the core or within that shell expansion, or within these supernova explosions that we'll talk about later on. You have this on Blackboard, and so you might want to kind of print it off and look at it. It just kind of tells you what's going on with our sun. But we're going to go ahead and describe that here right now. The other thing that you have on Blackboard that I'm not really going to spend all that much time right now talking about is exactly what these tracks are like on the HR diagram. We will certainly come back to that, but I'm not going to do it today. So if we talk about looking at that central core, it's that helium-rich core. Certainly have not reached the temperatures necessary to go ahead and start burning that. But when you do start that helium burning, that hydrogen burning in the shell, you dump energy back into the core as well as into the rest of the star. And notice that then goes ahead and increases that radiation pressure outward, which means my star is going to expand and then certainly go ahead and cool off. Now, a medium mass star, like I said, 0.4, 0.3, or up to 3, 4 solar masses. It just kind of depends on whose definition you're looking at. I tend to think we're going from about 0.4 to about 4. Once they exhaust that hydrogen, they're going to go ahead and swell up and become a red giant. But at this point, nothing has started burning yet. So they're just swelling up, okay, and turning redder because they are cooling off. Now, because no energy production is taking place yet, I've certainly got a little bit of that hydrogen shell burning, but gravity's going to take over, and gravity's going to cause everything to collapse. And gravity then is going to go ahead and heat everything up, which is when then you have that hydrogen shell burning started. Now, that expansion is going to cause the star's volume to increase. And if my volume increases for the same mass, then my density has to decrease. And as I said before, then that surface temperature goes ahead and cools off. Now, because of that increased volume, even though we have a lower surface temperature, this star has gotten much larger. And so therefore, just pure energy output means that that star is going to be brighter. That's why if I look in the night sky and I see Aldebaran or Arcturus or something like that, it shines as a really bright red star. It's not because it's hot, it's just because it is so big. Now, that core, that helium, is going to continue to collapse and get smaller until you have this opposing force to go ahead and counteract gravity. Now, at some point, that core is no longer going to be atomic helium. Because remember, guys, we have helium nuclei. We also have all these electrons that are roaming around. And so the helium nuclei is going to grab those 2 electrons and be atomic helium. But eventually, the temperature is going to rise enough, it's going to kick those electrons off. Also, the helium atoms have collapsed into what's called a stable electron degeneracy. Now, all that means is those electrons will be, electrons, remember, are negatively charged particles. So that means as all these electrons try and get together around the helium nuclei, they're eventually going to cause the collapse to stop because all these electrons are negative and they don't want to get close to each other. And so what happens now is the core, and of course then the rest of the star, is being held up by what's called electron degeneracy pressure. It just means that, I can't go ahead and compress the core anymore because the core is made up of electrons, and the electrons are exerting a repulsion effect. That's due to what's called quantum effects. If you remember your chemistry, something called the Pauli exclusion principle. And that says no 2 electrons can occupy the same energy state at the same time. And so once I get all those electrons into the lowest energy level possible, then they're there and they don't want anybody else sharing their same space. And so that's what we talk about when we talk about electron degeneracy pressure. Now, if you have a more massive core, then it can compress even further and have a smaller radius until you simply can't get those electrons any closer. Now, the URL that I have down there, guys, is one of a Nike commercial. I'm just going to go tell you to watch that one. That's kind of cute. And it does relate back to what I'm talking about with those electrons being in the lowest energy state possible. Now, let's go back to thinking about gases. A normal gas is going to expand when heated, but the problem is those degenerate electrons are not behaving like a normal gas. And so, they're not going to be affected by temperature, and even though I've got my temperature increasing within that core, nothing is going to happen. The only thing that's going to change is the electron's density. So, we've got that collapsing core. It's going to continue to radiate energy, so that potential into kinetic, but there's not going to be any change in the behavior of the core. And so you've really got kind of an unstable situation right here. So something may happen that completely causes those electrons to revert back to ordinary or normal electrons as opposed to the electrons in this degenerate state. We also know that a degenerate core is a good conductor of heat. And so remember, when you get that enough energy to go ahead and start converting helium into carbon, because remember, guys, the electrons are really close together, but we still have all that helium nuclei in there. Remember, we're still adding energy to the core. It's just that nothing is happening because you can't do anything with those electrons. At some point, the helium nuclei are going to have enough energy that they're going to start burning, and they're going to be converted into carbon. Well, because of the fact that that degenerate core is a good conductor of heat, because you're right sitting there on all those electrons, that's going to spread very, very quickly, all the way through the core. It's not going to cool by expansion because, again, you're still talking about degenerate cores of electrons, and those electrons are not behaving the way that you would expect them to. So that helium's going to heat up, and there's a reaction rate of temperature to the fourth. So whatever my temperature is, I'm going to raise that to the fourth power, and that's basically that energy that I've got coming out of there. And man, when you do that, that does indeed have enough energy to go ahead and basically ignite everything at one time. And notice, guys, what I said in parentheses, less than a minute. And that's then what happens when we talk about a helium flash. I mean, literally, it is over such a short period of time, and it just violently goes ahead and explodes. Well, that has enough energy in it to go ahead and promote those energies from the lowest energy states back up to outer energy level states, and they do go ahead and revert back to their normal behavior. So when you have this helium flash going on in these smaller, medium-sized stars, I mean, this thing does start with a flash, but it does occur so quickly that the rest of the star kind of sees it as kind of like a hiccup, and you don't really have a huge reaction to it because it does occur so fast. So, like I said, what happens is they fuse together to form beryllium, but that's not stable, and so you undergo this helium flash, and what happens is you have these three alpha particles fusing together to form carbon. Remember, guys, that 90% of the stars is 90% of the lifetime of the star is spent on the main sequence line, and so as we move off the main sequence line, they're going to start using this fuel up faster and faster and faster, so they're not going to spend a whole lot of time going from leaving the main sequence down to that final endpoint. And this is that triple alpha process. Notice that you get beryllium, but you add another helium to beryllium, and it goes ahead and forms carbon, and then carbon plus helium will go ahead and form oxygen. Now, you're not going to get a lot of oxygen formed, but you will just by random motion because of the really high pressures and temperatures in there, get that oxygen formed, but it's not going to be very much. And you do have, and guys, I'm sorry, that should be a plus gamma instead of an equals gamma. So it should be a 16 oxygen, plus a gamma. So notice that all three of those steps, unlike some of the others that we've looked at, all three of these steps produce gamma radiation. So you got a really high amount of energy that spreads through that core really, really, really quickly. And so the star is going to go ahead and, eventually, it's going to take a while, okay? Because like I said, it's almost like this little blip. And so the energy has to get radiated out. And remember, it takes a while for that energy to get to the outer layer of that star. It is going to go ahead and expand, and it's going to get brighter, and it's going to cool. Okay, remember, these are happening over millions of years, which for astronomical times is very, very quickly. And you can also see that carbon and helium will fuse to form oxygen, but that's not going to happen generally in a very large amount. But there will be some oxygen there. And, as we're going to go through these core burnings and these shell burnings, for a short period of time, you will indeed get equilibrium reestablished, but boy, it's not going to happen very long because, we're talking about these nuclei being more mass. So as they go ahead and convert to something else, I'm running out of mass a little bit quicker than what I did when it was just helium. Like I said, and this just what I was talking about with that outer layer not responding immediately, it takes a while for that to go ahead and do that. Now, very quickly, that helium is going to be used up and it's going to go ahead and stop. At that point, the core is going to go ahead and start collapsing. Remember, guys, it's always, a balance between that radiation pressure outward and gravity trying to collapse it inward. So now that core is going to go ahead and start to collapse because no energy is being produced. I've got the helium that's around the core, just like that hydrogen was around the core. So now I'm going to have helium shell burning. Star is going to get brighter and it's going to cool off again. And it continues moving then into that red giant region. So guys, we've got now the core, carbon, you've got helium shell burning, you've got hydrogen shell burning, and then you've got the rest of the star. And every time you get one of these bumps or one of these pulses, however long it may take it to get to the outer part of the star will respond and expand and cool off. Now, stars larger than 2 solar masses don't go through that helium flash. They do it more gradually. They're still burning helium, but they do it in a much more controlled way. And they basically head to that red giant region without any major problems. However, that core still does go through that degenerate electron core, and you still do have to go ahead and eventually build enough energy up to go ahead and kick those electrons back to their regular state. So you got carbon surrounded by that helium shell being surrounded by a shell of burning hydrogen. Now, the core is going to continue to collapse and release energy. The problem is these cores for these medium-sized stars are not really going to be large enough that they're ever going to reach the temperatures really required to completely convert carbon into oxygen. So that's just not going to happen. But what will happen is the core is going to continue to collapse, and you will go through these expansion and contractions and expansion and contraction, things like that. And so eventually what happens is the entire mass of the star, other than the core, basically, as these things get so big and get so far away from the core, will tend to basically leak off the star. And what you have left then is a core, and that at that point is a white dwarf. Because that core is going to continue collapsing, well, you're going to get back to that same problem with that degenerate electron, because that collapse causes those electrons to try and get as close and close and close as they possibly can to each other. And so that core is going to stop collapsing once you get all the way back to that degenerate electron state again. The other thing that gets produced from these stars is you have these winds that get produced, and so these winds will also carry off the outer layers of the star, because it's so far away, it's very, very easy to go ahead and pick those layers off because they're not held onto very tightly. So we get to the star, which is now called a planetary nebula. And we find that ultraviolet radiation heats that gases, and sometimes when you get ionization, you get these incredible colors associated with these planetary nebulas. And so this is a planetary nebula. You can see right in the center there's that core that's left that is continued collapsing because it can't go ahead and actually burn or convert carbon into oxygen, with any major amount in there. So everything continues collapsing until the core can't collapse anymore, which is back to that degenerate electron state. And then you get these outer layers that have been produced every time you have a pulse. And in some cases, too, you've got a rotational effect in there. You could have a binary star system, things like that, that are producing these incredible patterns. Here's another example of a planetary nebula. I mean, you look at that and you can easily see that you are talking about these pulsing states as they come out. I also think these things are just incredibly cool looking. These have nothing to do with planets, guys. Even though they're called planetary nebulas, they have nothing to do with planets. And you can see in the center of that planetary nebula, you can see what remains of that core, which is now a white dwarf. Remember, white dwarfs are going to be really, 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 really hot because they're the core, but they're going to be incredibly dim. The only way we can see a white dwarf is it's pretty close to us. It's another planetary nebula. The colors indicate the temperatures as well as the material itself, what chemicals are composed within those layers. This is another one that we're seeing from a little bit different vantage point, and it looks like that material then is just coming out basically on either side. In reality, you are talking about that material may not be as much in 360 degrees, but certainly there is some coming out at all angles. But you can almost look at this one and see those winds that are pushing that material outward that are coming from that outer envelope of those stars. And like I said, those white dwarf stars, just simply because of the collapse, are more of those degenerate electrons. And the greater the mass, obviously, the smaller its radius. Now, what do I mean by a small radius? Well, guys, white dwarf stars tend to be very, very dense. I mean, think about taking, that core of that star and collapsing it down into something the size of the Earth. So we are talking about huge densities. However, that's not as dense as some of the other things that we're going to talk about, like a neutron star, or heaven forbid, even a black hole. So these white dwarfs are eventually going to go ahead and cool and fade away. And that's where we think we're seeing these white dwarfs that are on the HR diagram, is they're from these planetary nebulas, not from the white dwarfs that are going to be formed from when those small little red dwarf stars finally go ahead and collapse and fade away. Now, we also think that we're going to talk about something called a nova and something called a supernova. And I said, remember, too, that we're making the assumption that the mass throughout this system is not changing. But we do know that there are instances out there where the mass does change. And if a white dwarf has mass falling onto its surface, then that can cause that star to become very active, and it will form a nova and can then go ahead and quickly release energy. And that star is going to become much, much brighter, and that's what's called a supernova type 1. When we talk about these really large massive stars going over into supernovas, then it's a little bit different behavior because of what's going on. But white dwarf does indeed have mass being added to it because of, pulling mass from, let's say, another star, then it can go ahead and go off as well. So our sun is going to become a giant, a red giant. Then it's going to form a planetary nebula, and in the center of that planetary nebula, we're going to have a white dwarf. Now, unfortunately, guys, as our sun goes ahead and forms that planetary nebula and forms that red giant, there's a good chance we probably are going to be inside the star. So you go outside, you'll have this beautiful day, you look up, and you're going to see our sun coming toward us. Of course, guys, that's not going to be for at least another 5 billion years. But, for the last a couple of seconds of the life of the Earth, it might be kind of an interesting picture to see the sun coming toward us. And not only coming toward us, but growing redder at the same time. So let's talk about these more massive stars. These are between 3 and 9, solar masses. And again, those are somewhat arbitrary numbers. 4 and 9 would work just as well. but they have that same kind of medium mass star, or they go ahead and evolve the same way as our medium mass star does until they get to that carbon there, because now they're large enough that when they collapse and the core collapses, they can go ahead and reach the temperatures and the pressures necessary to fuse carbon. In fact, we're going to find that they can fuse a lot of things. So the core contracts, becomes degenerate before carbon ignition is ignited, and so now you have carbon undergoing thermonuclear reactions, and that can form an implosion known as carbon detonation, and the temperatures can reach, as high as 600 million Kelvin. That's an extremely high temperature, guys. Now, in some cases, that's going to blow the star apart in a supernova explosion. Not always, though. If the star does indeed survive, it does so by forcing that core to go ahead and expand and remove that degeneracy, and then it's going to continue evolving the way a normal high-mass star would. So, as with everything, guys, some things, are not quite the way they are at other stars, and so you can just, at this point, blow these stars apart. During the supernova explosion, elements heavier than iron are going to fuse together and form the elements that we know of today, as well as in a lot of other variety within the explosions of these stars. And so, guys, everything that we see, every element out there was made in the interior of a star or through the explosions that are produced in the star, and that includes us. Most of the carbon that we talk about that gets formed within these stars is a carbon that we see that forms life. So, guys, you're actually made of stardust. So you really are a star. You just didn't know that. You're made of the dust that goes ahead and forms those stars. This is a picture of one of the distant galaxies. And this has got a picture of a supernova on it. Okay, so then your question is where? Okay, guys, if you look, there are several bright stars in here that appear to have spikes. Okay, most of those are stars within our own galaxy, especially the two big ones that you see in the lower part of the picture. The one right there and the one right there. Those are certainly stars within our galaxy. But guys, if I go over here and I look at that thing right there, right at the edge of the left side of the field, that's a supernova. And guys, that is within that galaxy. Okay? And we find supernovas a lot in other galaxies. We haven't seen as many of them in our galaxy. And part of it's because there's a huge part of our galaxy that we can't see that's simply obscured by gas and dust. So we feel like they're probably there, we just can't see them. And so a nice way to be able to view them is look at these other galaxies. Now, think how bright that particular star would have to be for it to be able to be seen, knowing that it's actually within this galaxy right here. Okay? Like I said, those are obviously stars within our galaxy. That one, however, is not. And so the question is, how do they know that's not? Well, you can look at the characteristics of that star. You can look at the spectrum of that star, and by that, looking at where that star is, and you find out that yes, indeed, based on those measured distances, that star is in their galaxy and not within our galaxy. So, guys, that's a whole lot of energy when that thing goes off. Now, this is an old remnant of a supernova, and when these things go off, if they're close, and we've had several go off in ancient times that certainly were bright enough to actually be seen during the day. Can you imagine going out inside and looking up and all of a sudden you see something that is bright enough to be seen during the day against the backdrop of the sun? So you can see that this one obviously is very old and it has expanded out quite a bit. So if you kind of take that back all the way toward the center, you can see that at one time it certainly then was met at a point. This is one of the newer ones, the next couple of ones that I have. You can see how different this one appears compared to that one. I mean, a huge difference. This one is obviously very new. This one is, and the next couple of ones are artificially colored to bring out the different chemicals that you see within the supernova explosion itself. Same way, this one is certainly color-coded to bring out the different chemicals as well as the structure of the supernova. And you can see that that star just looks like it blew itself apart. Now this one is colored artificially, but not so much to bring out the different materials. This one is color-coded relative to the type of energy you're looking at it with. You've got visible light in there, you've got infrared light, and then that blue light is looking at the X-ray spectrum of it. So again, if we're looking at the X-ray spectrum, there's a whole lot of energy associated with that. And you can see how tightly compact they are, which, gives you a feel for how old they are. And these are certainly under 1,000 years. And then this is the Crab Nebula. This is probably one of the more famous of the supernovas. And right at the center, there's something called a neutron star that's rotating and pulsating. We'll talk about that here in just a minute. But you can see the expansion rate of that. I mean, the incredible detail that the Hubble telescope gives us of this incredible picture. You can just see that kind of blew itself apart. Now, unfortunately, in this picture, we cannot see that central core. We cannot see the pulsar. But we can measure it in radio waves, and we know it's there. So these very high-mass stars, like I said, are masses that are greater than 9 solar masses. And these stars are simply so hot, that carbon ignites before that gas can really become degenerate. And so that carbon fusion turns on gradually. So guys, this is just kind of a continuum going from those really small mass stars to the really big mass stars. So those stars go ahead and continue to fuse heavier elements for a while. But again, it's not a very long time because, again, you're now fusing larger and larger and larger nuclei, so it doesn't take nearly as long to go ahead and use up the mass within that core. Now, we finally get to the point that you have an iron core reached. Everything has been burned through thermonuclear reactions up till iron. And when you burn it, you always have energy released. Unfortunately, when you reach the iron, you can't go ahead and get energy out of burning iron. It does not undergo an energy release when it fuses. So what iron does is it goes ahead and breaks down. So basically everything stops. So guys, if you're not having any energy produced, you know what happens. That core goes ahead and collapses because gravity pulls it in. And then what happens when that core collapses? The rest of the star goes ahead and falls into that core, and then it rebounds out. And that's in what you were seeing with these things right here. Those supernova explosions are really formed when you reach that iron core, the energy stops, gravity takes over, the core collapses, and the rest of the star suddenly has nothing else to hold that star up, and so it falls inward as well. Well, it reaches that core and rebounds, but in the process of reaching that core, it goes ahead and causes that core to collapse, and there's enough mass on the rest of these really high mass stars that you actually go ahead and collapse the core down to what's called a neutron star. Now, remember, guys, a white dwarf was composed of degenerate electrons because you had these negatively charged particles that maintained then a repulsion effect. Well, there's enough mass contained in these really massive stars that when they collapse down onto the core, that those electron degenerate pressure can't hold up anymore. And so everything gets pushed together. Now remember, within the core, you also have atomic nuclei, okay, and you have protons, and so the protons then get run into by then an electron and a proton then make a neutron. And neutrons are neutral, so because they're neutral, there's no repulsion effect, and so everything then can get really close together. And that's what's going on within these neutron stars. It's the core of the star that went into a supernova explosion, and in that process, collapsing that core down. Neutron star is composed of neutrons, obviously. They're also known as pulsars because they are pulsating radio sources. Let's go back to the conservation of angular momentum. Remember, guys, that if I decrease my mass and bring it in closer to the axis of rotation, that star is going to go ahead and speed up. Well, that's exactly what's happening with this core. I now have a really, really, really small core, okay, and so it's going to spin very rapidly. I mean, these neutron stars, because they're made out of neutrons, they're incredibly dense. Notice, guys, you're taking a core, from a really, really, really massive star, and you're taking every bit of that mass and you're putting it into an area the size of a small city. Think about a small city here in the United States. And I do mean a small city. So those things are rotating very, very rapidly. We know they have magnetic fields, and so that pulse tends to come out through either one of those poles. And if we happen to be, in the direction of where it's rotating, we'll intercept that radio wave. We saw the same kind of bipolar flow out of stars that were forming. Remember I showed you a picture of that bipolar flow from a star? It's coming out along the magnetic field lines, right there where those field lines then come down to the surface of the core itself. When these things were originally found, they were so exactly on step that it was assumed that they were artificial, and they thought it was, the first kind of contact we might have had with whoever might be out there. And they were called LGM sources. They were LGM. Now, what do you think LGM might stand for? Did you come up with little green men? That's what the LGM stood for, because they were, we hadn't measured anything like this before, and they were so, absolutely so precise that we did think they were some kind of artificial intelligence out there. Little green men, and no, guys, they're just nature. Just happens to be really precise and rotating at a very, very, very precise rate. Although we do know, having observed them now for a while, that they will go ahead and eventually slow down. So, for these really high mass stars, you've got supergiants, you got supernovas, and you got neutron stars. But we know, guys, there are even more massive stars. These really, really, really big massive stars. And the core reaches iron just like they did before. Fusion's going to stop simply because of the fact that you can no longer burn fusion through thermonuclear reactions. But these are really massive stars, and so they're going to go ahead and collapse. But the problem is they are so massive that when they hit these cores, they get down to the neutrons, and the neutrons still can't go ahead and hold up the rest of the core, and so the core just continues collapsing. Now, as the core collapses, remember the rest of the star has hit that core, it's rebounded, so I'm forming these same type of supernova explosions I just showed you. But what really gets interesting is what's happening in the core. White dwarfs composed of neutrons, degenerate electrons. Neutron stars composed all of neutrons. Well, I could have gotten really close with those neutrons, but when I talk about these really massive stars rushing in, hitting the core and rebounding, that core is simply continuing to collapse. And in fact, it collapses basically so much that it winks out of our universe. Okay, guys, what are we going to call that? Well, these really massive stars go from a supergiant, a supernova, into something called a black hole. And you can think of a black hole as a really, really, really strange object. A black hole basically is a place where a star used to be. That core simply has winked out of our universe. Now, let's go back to Einstein for just a minute. Einstein said that mass curves the space around it, and that really you don't have one without the other. And the more massive the object, the greater the space is curved. Now, when Einstein came up with this was the early 1900s, he didn't really have a way of showing that that was true. However, the solar eclipse of 1919, he was able to get out there and go ahead and actually do the measurements showing that this was true. Guys, if I could take a side note, I would go ahead and send you out to look at Einstein's life and what his was like after he went ahead and showed that Newton was wrong and that space and time really are tied up with each other. Now, this is kind of a way of trying to show you what's going on. If you just take a membrane that's kind of stretched and you roll the Earth there, notice that you're going to go ahead and kind of that pucker in space, you're going to kind of show where that mass is. Well, if I could make that even more, more massive, then that pucker in space is going to go ahead and, even be compressed or even a little bit more down into space. And Remember I said that what Einstein did was show that light was, try this again, guys, that space was curved if I went by a really large mass? Well, what Einstein did during that solar eclipse is you knew where the position of a star was without the sun being there. Then he measured during a solar eclipse the position of the star as that light came toward the sun. And what happens is the light was physically bent around because it was traveling through that curved space. And so you had different positions of where then that star was. Well, we know that can't be right. And so the difference was the fact that you were indeed curving around space. And so you can see here light is deflected from its original position or path simply because of the fact that it is traveling through space and space is curved. Now, as you proceed into a black hole, weird things are going to start happening. And it's very easy to listen to what's happening. It's very hard to understand exactly what's happening. And these are physical reactions to curved space when you are then getting toward a very large mass, like a black hole. And we will come back to black holes when we start talking about what's going on at the center of galaxies within the next unit. And so Einstein talked about relativity. And he said that as you get closer to a black hole, or as you proceed where your speed is increasing and now you're an appreciable amount of the speed of light, 3 times 10 to the 8th meters per second, or 186,000 miles per second, your time is going to slow. And these are physical reactions, guys. These really do occur. Your time slows down, and those are biological times as well. Length is going to contract in the direction of motion, and your mass is going to increase. So time is going to slow down as you increase your speed. Length is going to contract in the direction of motion, and your mass is going to go ahead and increase. Now, we know that black holes exist. Now, when I first was an undergraduate here, black holes had not been discovered yet, and I did a readings for one of my professors because I was interested in them. I had read about them, and at that point they were still theoretical objects. And so he was willing to let me read about them, but he kept saying just wasn't sure they really existed. Well, nowadays, guys, we know that Cygnus X1 does exist. That was the first black hole that was found. This is the constellation Cygnus. It is running through the Milky Way. It is looking like a swan. And you can see there's some other things there that are kind of interesting, but we're basically looking at Cygnus X1. And so when I go ahead and look at that point in space, I see a star, and then I don't see anything. Which makes sense, guys. If it's a black hole, that thing has curved space so much that light can't even escape. So the question is, how do I then indeed see, and I'll put that in parentheses, a black hole? Well, you see a black hole because of the influence it has on a star going around it. And what happens, and this is not a picture of an actual Cygnus, this is just an artist's conception, but it shows very well what happens. If you have a star that's in a close approximation within that black hole, you're going to find that that star is basically going to be pulled toward that black hole, and it's basically going to be pulled apart. And as that star is being pulled into that black hole, you have X-rays given off, you have all kinds of energy that is given off as that star is being accelerated into that black hole. And so what we look for is we look for a star that's being ripped apart that seems to be falling into nothing. And that's how we go ahead and find a black hole. Like I said, we're going to come back to those really large black holes that are at the end of the evolution of these really, really, really massive stars because they have a definite influence on what's going on within the center of our galaxy. But we will do that in the next section. So guys, this was kind of a short journey. Granted, it took us about 50 minutes, but short journey through looking at the evolution of these stars. You will see on Blackboard, I do have some more information there for you that I've tried to lay out, looking at an HR diagram and exactly what those tracks are, things like that. So I would certainly encourage you to print that off, and then we will have one section, during our time that we do talk about the evolutionary tracks and show you what's going on relative to the HR diagram. And before you go ahead and join me next time, please make sure that you have gone on to Blackboard and pull down an outline of what's going on with all of these so that we can kind of have those in front of you as we go ahead and talk about really what's going on within the core of the red dwarfs, stars like our sun, really large stars, and then these incredibly massive stars. And with that then, we'll go ahead and finish looking at stars, and then our final unit will deal with galaxies and beyond. So with that, guys, I'll talk to you next time.